I want to give you one interesting little tidbit on how to exploit symmetry in calculations. Okay, so the symmetry in calculations of joint PDFs and all that is very, very important. Quite often a lot of work can be simplified if you do symmetry. Okay, so let's say you have x1 and x2. So usually symmetry will come from independence also. So let's say these are independent, uniform in 0 to 1. Okay, so let's say somebody gives you this independent, uniform, 0 to 1. So if you look at it, the region of support is this guy, right? I'm sorry, 0, 1, 1. This is the region of support. Support is uniform, right? x1, x2. Okay, so now if you were to ask this question, probability that x1 is greater than x2. Okay. Okay, so somebody might ask you this question, it's continuous distribution, and you want to find probability that x1 is greater than x2. So the first thing you should do whenever somebody asks you a question like this is to plot this region in the region of support, right? So this is what you would do. This is x1, this is x2. So x1 equals x2 is this line. So everything on this side will have x1 greater than x2, right? So couple of things to remember about these continuous distributions is probability that x1 equals to x2 is actually 0. Okay, so think about why that has to be true. You have infinite precision double two-valued distributions, and taking two different real numbers, and you cannot have x1 equal to x2 with non-zero probability. So this will be 0 probability, and you have x1 greater than x2, and so these two are x1 and x2 are independent. They're both the same. Whether you change x1 or x2, nothing is going to change. So if you look at it very, very carefully, this region is x1 greater than x2. What about this region? This region is x2 greater than x1. Okay. So if you want to do probability of x1 greater than x2, one method is to do a double integral. Okay. Go from x1 from 0 to 1, x2 from 0 to x1, and do the integral. You will get an answer. I'm not saying this is very hard, you can do this quite quickly. But you can also observe that probability of x1 greater than x2 has to be equal to probability that x2 is greater than x1. This is where the symmetry comes in. Okay. In the distribution, there's nothing to distinguish between x1 and x2. If I just flip x1 and x2 around, I call x2 as x1 and x1 as x2, nothing is changing, right? So that's the independence assumption. That's very important in the symmetry. Okay. So the distribution is invariant to switching x1 and x2. So here also, if I switch x1 and x2, the probabilities will not really change. It should be the same probability. Just the region will change, some nomenclature changes, nothing else changes. So since these two are equal, and what will be the sum of these two probabilities? Probability of x1 greater than x2 plus probability of x2 greater than x1 plus probability that x2 equals x1. This needs to be equal to 1. So this is like everything, right? So the entire region of support can be split into the region where x1 is greater than x2, x2 is greater than x1, and then x2 equals x1. So these probabilities have to add up to 1. So now this I saw as 0. These two are equal. So what should be the value of each of these guys? The value of each of these guys should be equal to half. Now in this situation, it's quite easy to evaluate this integral, and you can check that it's half. But things can get a little bit more confusing if I have 3 or more independent uniform distributions. Okay. And then people will ask you for some probability like this. What's the probability? So usually it's worded in English. They will ask, what is the probability that x1 is the largest? Okay. So now, so what is the meaning of x1 being largest? x1 largest is equivalent to x1 greater than x2 greater than x3. So now if you notice all the equalities, so you can also have a situation where x1 equals x2 greater than x3, but all those equalities I don't have to consider in a continuous independent distribution, because all those guys will have probability 0. The moment I put equality somewhere, I'll have probability 0. Okay, so for instance, if you say probability that x1 equals x2 but greater than x3, this is 0. So anywhere I put equality, probability will go to 0. That's the nice thing about independence and continuous distributions particularly. I'm sorry. So this is the region for x1 greater than x2 greater than x3. So of course you can write a triple integral here. It's not very, it's not really that hard. You can write a triple integral here. The joint distribution is 1. Right, so you can imagine how you'll write the triple integral here. So all these cases are between 0 and 1. Okay, so you write integral for x3 from 0 to x2, then x2 from so you can write a triple integral. I won't go into the details there. It's a bit confusing and you can get messed up a little bit. But then one can use symmetry. So how do you use symmetry? So the way to use symmetry is, if you look at the entire region, there's a region of support, you split it into various things like this. So something should be greater or lesser, right? So you pick any point, x1, x2, x3, there will be a certain ordering. And if you look at all possible orderings, all of them have to be the same, because the probabilities of each of them should be the same. So that's the critical idea here. So what are the various different orderings possible? You can have x1 greater than x2 greater than x3, or you can have x1 greater than x3 greater than x2. So remember, it's critical that any equality I don't have to consider. If you have to consider equalities, things will become more murky. Okay, so this is a possibility. The other possibility is x2 greater than x1 greater than x3. The other possibility is x2 greater than x3 greater than x1. The other possibility is x3 greater than x1 greater than x2. The other possibility is x3 greater than x2 greater than x1. Okay, so there are 6 different possibilities here, and then additionally some more equality possibilities, more possibilities with equality, but all of them will have probability 0. All of these guys have probability 0. And the point is, each of these guys have to have the same probability. This is a crucial thing to understand. Okay, they all have the same probability. The reason is, there's nothing to distinguish between 1, 2, and 3. I just flip 1, 2, and 3 around. I should get the exact same distribution because it's independent and it's uniform in the same interval. Okay, so all of these guys have the same probability, and they have to add up to 1. So what will be the same probability? That is equal to 1 by 6. Each of these guys is probability 1 by 6. So what's the probability that x1 is the largest? In 2 of these cases, x1 is the largest. So this will work out to 1 by 6 plus 1 by 6, which is 1 by 3. Right? So these 2 cases will add up to x1 being the largest. Okay? So you can also ask any other question. For instance, what's the probability that x1 is in the middle? Okay? Right? x1 is sandwiched between x2 and x3. So you see that is again 2 cases. Again will be probability 1 by 3. Okay? You can ask for a specific ordering. So any ordering when you have these kind of independent distributions is easy to calculate. Okay, so this is one use of symmetry. The other use of symmetry is also in calculation of expectation. Now we also saw one of the critical properties of expectation was expectation is linear, right? A linear operation over addition. Okay, so supposing this is a very interesting question. So you have n independent identical distributions. Okay, somebody tells you, and they are also continuous. Okay, so let's say we'll assume it's continuous. Okay, I'm not really sure if this continuous is needed, but for now let's just take continuous. It doesn't really matter. So one of the questions that people would ask is this expected value of x1 divided by x1 plus x2 plus xn. Okay, so for instance, continuity is sometimes needed to avoid some dangerous situations of all of them going to 0, etc. So we'll assume these things exist in some sense. Okay, so when you do this calculation, I've not told you anything more. I haven't told you anything about the what the distribution is, this, that, and etc. But then one can use symmetry and the fact that they are independent, symmetry that comes from the fact that they are independent and the linearity of expectation to evaluate this expectation. Okay, so you might be surprised by how that will work out. The crucial point to observe is expected value of x1 divided by x1 plus x2 plus so on to xn is actually the same as expected value of x2 divided by x1 plus x2 plus xn, which is actually the same as, let's say, x3 by x1 plus x2 plus xn, and it's actually same as expected value of xn divided by x1 plus xn. Okay, so this comes from symmetry, which in turn comes from the independence, identical nature of the distribution. Okay, so this is the first observation you make. And then the next observation you make is, if you add up all these expectations, what will you get? If you add all of the above, okay, what do you get? They're all equal, so you will get n times expected value of x1 by x1 plus x2 plus xn, right? They're all equal. If I add all of them, I'll get n times this. But you can also add them the other way around, right? So what is this? This is just expected value of x1 by xn plus x2 by xn plus xn by x1 plus xn. Okay, so you can see why this is true, right? So this is by linearity of expectation. Expectation distributes over addition, so if I add them n times, I get this. No, but what is this guy inside this? What is this guy? This guy is just 1. And what is expected value of 1? It's just 1. So what is expected value of x1 divided by x1 plus xn? Just evaluates to 1 by n. Okay, so without doing any major integration, you've got to the answer. So quite often, while integration is an obvious way of getting to the answer, if you use symmetry, independence, linearity of expectation, you can avoid a lot of hard work and get some very simple and elegant answers to calculations involved. So a lot of probability is simplified by this. Okay, so I'll stop with this as far as this lecture is concerned. This lecture showed you how to deal with expectations, how to do these calculations of expectation when you have continuous distributions, one variable, two random variables, how to look at region of support, etc., and how to exploit the symmetry of the given situation, in particularly when you have independence and identical distributions, how to exploit symmetry to simplify your calculation and quickly get to the answer. Okay, so I'll stop here for now. Thank you very much.